When it comes to spherical coordinates, there's always something that bothers first-time learners of it, and that is the possible maximum ranges for theta and phi, respectively. So this whole video is going to be about theta and phi. So this is going to all about theta and phi. So when it comes to theta and phi, there's a few things we want to keep in mind. In particular, let's talk about theta first, because theta was here before spherical coordinates, because really the theta that's being used in spherical and in cylindrical coordinates is exactly the same theta that you learned in Calc 2 for polar coordinates. So in polar coordinates, if we have a point x comma y, we can think of this as a distance r and an angle formed with the positive x-axis to give us another pair of two real numbers, r and theta. So you can take a Cartesian coordinate pair, x comma y, and rewrite it in a different coordinate system, r comma theta, where r and theta are described in this diagram. Now, because of this, theta definitely the smallest it can be is 0, and then the biggest it could be is 2 pi. So now there's different things where people might say, parentheses here, because really you don't need 2 pi if you have 0, because you can just, instead of using 2 pi, use 0. So technically, this is a valid statement. But it's not necessarily that it has to be this range. The important thing really to emphasize here is that in polar coordinates, you don't need a range bigger than 0 to 2 pi. You only need an interval whose length is 2 pi, starting from some number and ending at that number plus 2 pi. That interval there will allow you to talk about all points in the xy plane. So, and of course, in this case, r would be 0 to infinity. That seems to make the most sense. This doesn't mean we can't have crazier point values, like can't we have an r value of like -2 and, maybe 9 pi over 4? Isn't that possible? This right here is bigger than 2 pi. And this is, well, of course, this is negative. It's perfectly fine to have those numbers as well, but we're not going to be talking about those examples in here. The important thing that I really want to focus on is the fact that theta really just needs an interval of length 2 pi. So if we move on now to spherical coordinates, let's move on to spherical. And in spherical coordinates, or x, y, and z axes, we know that a point, let's say right here, this point here, x comma y comma z, can be labeled by a rho, where rho is the distance to the point from the origin. So draw a straight line from the origin. The distance of that line is rho. Theta, which is, if you imagine dropping this point down into the xy planes, wherever its shadow is, then drawing a line from there to there, straight line from the origin in the xy plane, that line has a length of r, and the angle it forms is theta. And lastly, you have phi, where phi is the angle measured from the positive z-axis. There you go. So there's where everything comes from. This r isn't actually used in this spherical description, but it does connect it back to polar, so that's why I just wrote it. It's the same r. But really, these three numbers are what give us the ability to write this Cartesian triple xyz into spherical coordinates. Okay, so we already know that since this theta is exactly the same theta as in polar coordinates, we know that theta can range from 0 to 2 pi. And I'm just going to put brackets and not do the parentheses because while technically you don't need to double count, when you're doing an integral, whether or not you make it a parenthesis or a bracket doesn't change the value of the integral because it's a single point. But enough of that. It's a little bit more technical than what we need. So with that being said, let's now think about phi. What should the maximum range for phi be? Now, you might want to argue that, or you might just assume that, shouldn't it be 0 to 2 pi as well? And the answer is going to be no. It's going to be 0 to pi. Why is that? Well, let's consider a hypothetical scenario here. So let's go ahead and just delete this information here. And let's just think about a point in the in 3 dimensions here. So let's just bring this up here. We can talk about that later. So let's draw a point. Here's a point. I'm going to make it in the xy plane, but I'm going to put it let's put it over here. So it is in the xy plane. I know it looks like it's floating above the xy plane, but let's just say it's right there. So the coordinates of this point, I'm going to give it to be, well, let's say it's a distance 1 from the origin in the xy plane. So we know that the rho would be 1. The theta, well, this is all the way around this way. So that is, well, this would be pi over 4, 3 pi over 4, 5 pi over 4. So let's say this is 5 pi over 4. And then phi is the angle, is this angle here. Well, since this point lives in the xy plane, this angle here has to be a right angle. Even though it doesn't look like it due to the perspective, this is a right angle, because if this point lives in the xy plane, then this line segment connecting it to the origin must also live in the xy plane. And we know that the z-axis has to be perpendicular to any line living in the xy plane. So this angle here has to be a right angle. So this would be pi over 2. Let's move this around a little bit to get some room, but there's our point. Okay? But isn't there another way that we could describe this same point? There absolutely is. Couldn't I say that this point here is the same thing as, let's say, 1 comma pi over 4 comma 3 pi over 2? So in this case, what we're doing is we first think of distance of 1. So let's say this is 1, unit of the distance. And we're going to rotate out pi over 4 to get here. Well, to do this perspective-wise, let's say it's right here. Okay, so this is pi over 4. Distance of 1, there's our point. And then this 3 pi over 2 is saying rotate, this is pi over 2. Rotate again, so now we're down here at pi, and then rotate again to get back up to the xy plane to get 3 pi over 2. So these two triples describe the same point. But notice here we had to allow phi to go beyond pi. So really, whenever we do this restriction here of phi, its maximum domain being 0 to pi, it's really to just eliminate the possibility of these kind of redundancies. If we keep things restricted to this, and if we want to be super, super, super technical, something like that, then every single point in three-dimensional space has a unique representation. It's all about being unique. We don't want multiple distinct addresses referencing the same point. So the important takeaway here is that the maximum range of theta is 0 to 2 pi, and I'll go ahead and put that on there. And phi, its maximum range is 0 to pi. I'm not going to put a parenthesis on the bracket on pi here because pi and 0 do not represent the same thing. So, all right, that's the takeaway here.